Good day, I'm Norman Wildberger. Today we're going to look at the deep structure of the rational numbers. The rational numbers have a very interesting and rich structure that goes beyond what's usually studied in schools and universities, but really ought to be much wider known. This is important for us for a number of reasons. First of all, because the rational numbers are the framework in which this attempt to create real numbers starts out, where we try to create real numbers as Cauchy sequences of rational numbers. So the rational numbers are providing the framework for this game to be played. It's a game that doesn't work, I claim, but we need to understand all aspects of the game, especially how we start. The rational numbers are also important for us because ultimately I'm going to try to make the case that the rational numbers are the heart of mathematics. When we do mathematics, the rational numbers should be almost always foremost in our mind. We can do analysis and differential geometry, differential equations, algebraic geometry, combinatorics, number theory, who knows what. We can do it with rational numbers. We do not need real numbers. This is a point I'm going to try to slowly make as time goes by. So the rational numbers are really the heart of mathematics, and I think this is a major reorientation of mathematics in this coming century. Very, very important. All right, so let's review some basic things about rational numbers. First of all, here's the type that I give it, RAT. A rational number is a pair of integers, a over b, where b has to not be 0. We have this very crucial property of equality when two rational numbers are the same. A over b equals c over d precisely when AD minus BC equals 0. Or in other words, when this times this equals this times this. We have this alternate, somewhat more familiar notation. Instead of writing the bar slanted, I'll often write it straight like this, which is more convenient if the numbers are big. We have a notion of positivity of rational numbers. On the number line, well, everything that's to the right of 0 or including 0 might be called positive. And a over b is positive precisely when a and b are both positive integers, or when they're both negative integers. And it's that notion of positivity that is ultimately responsible for the order structure of the rational numbers. The fact that we can say that r is less than or equal to s. That means that s minus r is positive. Allows us to compare any two rational numbers and say which one is bigger, which one is smaller. And then of course we have the four main operations, which all students of mathematics ought to learn very well. And it takes some serious dedication to become familiar with arithmetic, with rational numbers, and it's very important. It's probably the most important thing for primary school students to master. The arithmetic is concrete and precise. We can say exactly what an answer should be. We can check to make sure that someone's made a calculation correctly. If I want to add 2/3 and 1/4, I have to do some work. 2/3 plus 1/4, I have to get a common denominator of 12. So that's 8 12s plus 3 12s. That's going to be 11 12s. So 2/3 plus 1/4 is 11 12s. And probably I should check that 11 over 12 is actually in reduced form. In other words, if there's no common factor. If there is a common factor, I should remove the common factor to get it into reduced form. That way we can easily check that a calculation has been done correctly. Compare that to the situation with so-called real numbers. It's like a night and day difference. With real numbers, one is talking all the time and rarely actually computing. As I've mentioned to you many times before, if I ask you what pi plus e is, There's no corresponding actual rolling up of the sleeves and getting down and making some calculation as there is for rational numbers. It's simply an empty kind of, well, pi plus e is pi plus e. That would be ridiculous. That would be like asking a primary school student what is 2/3 plus 1/4 and getting the answer, well, the answer is 2/3 plus 1/4. Such as the vacuity of real number arithmetic. Okay, so there is the rational numbers. Here is our standard geometrical understanding of it along a number line. We want to go now further today. We want to understand the deep structure of the rational numbers. Since the number line is rather large, it's nice to focus on just one part of it to try to delve more deeply into the structure. So let's have a look at the interval 0, 1, which contains fractions of the form a over b, where both of them are positive integers, and a is less than or equal to b. For example, 0 over 1, 1/5, 2/5, 3/5, 4/5, 1 over 1, which is the same as 5 over 5. Here are all the multiples of 1/5, all the fractions between 0 and 1, whose denominator is 5. And an obvious statement to make is that there are an unending number of rational numbers in this interval. Unending meaning that we can always add some more that we haven't already listed. If we try to list all the rational numbers in 0, 1, we do not end up finishing. There's always more to be added. Maybe we could say that there's an infinite number if we have a metaphysical orientation. But it's probably best just to say that we can keep on adding more and more and more and more until we run out of memory or run out of room or run out of time. For example, an unending sequence of rational numbers in the interval is 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Starting here, then 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, and so on, getting closer and closer to 0. Clearly there is as many of these as there are natural numbers. So even though the interval 0, 1 may look relatively small, it contains within it sequences of rational numbers that are just as big or just as unending as are the full sequence of natural numbers, which we usually think of as trailing off beyond our view. So it's a very rich object, this interval 0, 1 of rational numbers. So here now are two theorems that tell us a little bit more about how dense the rational numbers are in this interval 0, 1. The first theorem is that if you have any two rational numbers, r and s, then the average, which is defined to be r plus s divided by 2, that lies between them. Meaning that, for example, if r is less than or equal to s, so if this happens to be the smaller one, then this number r plus s over 2 is between r and s. In other words, it satisfies that inequality. As I'm going to be doing increasingly as we move on to somewhat more sophisticated topics, I'm going to give you these kinds of things to check as exercises. So we're not going to go through the details of things like this. They're relatively unproblematic. Give you a good chance to practice your algebraic skills. This, of course, is pretty obvious intuitively. You have two numbers, like 3 and 5. The average is 4, which is between them. This second theorem is along the same lines, but it's somewhat less familiar. It concerns two positive rational numbers, r and s, and we're going to assume that r is equal to a over b and s equals c over d in reduced form. And I remind you that that means that there are no common factors and that b is positive. So no common factors between a and b, no common factors between c and d. Now the mediant of these two rational numbers is this expression. It's a plus c over b plus d. we've added the two numerators and divided by the sum of the two denominators. Now, sometimes mistakenly, young students think that this is the way to add fractions. This is definitely not the way we add fractions. But this operation is still quite interesting. And this theorem asserts that this mediant lies between the two rational numbers r and s. So for example, if a over b is less than or equal to c over d, then the mediant is sandwiched between them. Very nice property. So there's two ways of finding a rational number between two given rational numbers. We can take the average, or we can take the median. But we need to have the rational numbers in reduced form to be able to make that work. There's a much more general idea that extends the idea of an average. This is the idea of a weighted average. And this is also a very important understanding. So first, let's observe that if we have a rational number, lambda, between 0 and 1, then also 1 minus lambda is between 0 and 1. All right, so now we have this theorem. Suppose we have two rational numbers, r and s, and they can be any rational numbers. And let's suppose that r is less than or equal to s. Then for any lambda between 0 and 1, this particular combination is between r and s. The combination is 1 minus lambda times r plus lambda times s. So the two coefficients that we have here are both in the range 0 to 1, and they happen to add up to 1. This is often called a convex combination, some kind of weighted average. In the special case when lambda is equal to a half, then this becomes just the average of r and s. So the picture that we have here is, here's our number line, and here's some rational number r and another rational number s. And over here I have the interval 0, 1, which of course is also on this number line, but it might be to the left or it might be to the right some ways, so I just put it over here. And we're imagining some number, lambda, which is between 0 and 1. Then given such a lambda, what we can do is we can take this combination, 1 minus lambda times r plus lambda times s. And that turns out to be a number between r and s, which has the same sort of proportional relationship to r and s as does lambda to 0 and 1. So for example, if lambda is equal to a half, then we get exactly midpoint. When lambda is a quarter, then we get a number that's over here. That's 1/4 of the way along. That's 3/4 r plus 1/4 s. On the other hand, if lambda was 14 over 15, let's say, in other words, a value pretty close to 1 over there, then the corresponding convex combination is weighted towards s. So it's in the ratio of 14 to 1. So you can see that in the extreme case when lambda equals 1, we recover s. And when lambda equals 0, we get r. And so as we move lambda from here to here, this combination runs from here to here. And this is a way of matching up any two intervals. This is a fabulous aspect of rational numbers, that in fact any two intervals pretty well look the same, even if one interval is very small and the other interval is very big. To make that a little bit clearer, let's consider this convex combination of r and s. Let's call it T. If we solve for lambda, well, we can bring the r that's on this side to this side, giving us T minus r. And then the remaining terms here we can factor as lambda times s minus r. S here, the minus r there. And then we can solve for lambda. Lambda is then T minus r over s minus r. And we see that so long as r is less than s, in other words, that they're not equal, this denominator is not going to be 0. So that means for every t in rs, we can solve for lambda. In other words, we can find the lambda so that t can be written as a combination of r and s. It's not hard to see that this lambda is actually between 0 and 1. I'll leave that to you as an exercise. So what that's telling us is that if we have an interval, say r1, s1, then every point in this interval, every rational point, of course, which is the only kinds of points we're talking about, every point in this interval or every rational number between r1 and s1 is matched up to a number lambda between 0 and 1 through this correspondence, through the correspondence that takes lambda to the combination 1 minus lambda times r1 plus lambda times s1. So this works both ways. Given a lambda, we can find this number t, and given a t, we can solve for the corresponding lambda by using this relation. So this is a complete matching up between points or numbers in this interval and numbers in this interval. Now, I don't want to frame this in terms of sets. I don't want to say that this set has the same size as this set, because there's arguably an infinite number of things in these sets. That to me is not proper mathematics. I'm simply making the statement that for every rational number here, we can associate a rational number here, and conversely, for every rational number here, we can correspond a rational number here. So there's a pairing up or a matching up of rational numbers between this interval and this interval. And the size of this interval is immaterial. Here's a much smaller interval, r2, s2. And exactly the same story applies. This interval 0, 1 is still in correspondence with this smaller interval r2, s2. So this number lambda here still corresponds to that combination 1 minus lambda r1 plus lambda s2. So as a consequence of that, we see that arithmetically all intervals are the same. This interval is completely matched up with 0, 1. This interval is completely matched up with 0, 1. So it follows that these two intervals can be matched up. We can associate to every rational number in this interval a unique rational number in that interval. And conversely, given one here, we can go back here. And we can do that sort of via this intermediate lambda in 0, 1. So the idea of the size of an interval is a little bit illusory. Small intervals have just as much complexity in them as do large intervals. By subdividing an interval into smaller intervals, we are not really getting something that's simpler. The complexity level is still there, even if we've magnified quite a lot. So the rational numbers have this cascading or kaleidoscopic aspect. As you magnify, what you see is pretty well similar to what you got at the higher level. So it's sort of infinitely divisible, infinitely rich as we magnify, as we go down and look at more and more closely at smaller and smaller intervals. And that, of course, gives us some justification for studying the interval 0, 1 very carefully, because if we understand that interval very well, then we can pretty well understand any other interval too. So let's have a closer look, a deeper look at the interval 0 to 1. So we're talking about rational numbers which are bigger than or equal to 0 and less than or equal to 1. Let's start listing some of these rational numbers. The simplest ones are 0 and 1 themselves. And if we write them as fractions or rational numbers, we get 0 over 1, 1 over 1. And here's a picture of just those two. They are the endpoints of this interval. All right, the next thing that might occur to you is to divide the interval into two pieces. So introduce the midpoint, a half. Now we have 3 points, 0, half, and 1. If we write them out sort of in standard form, 0 over 2, 1 over 2, 2 over 2. Then another thing we could do is we could divide the original interval into 3 equal pieces. giving us 0 over 3, 1/3, 2/3, and 3 over 3, or 1 again. Or we could divide into 4 equal pieces. 0, 1/4, 1/2, which is the same as 2/4, 3/4, 4/4. Or into 5 equal pieces. 0, 1/5, 2/5, 3/5, 4/5, and 1. And it's clear that we can carry on this way, and eventually every rational number in this interval will appear at some row as we go down. And typically it's the denominator that tells us what row we should be at. The bigger the denominator, the further down in this tabulation the rational number will appear. Also, there's duplication, however. This is not a unique list. So, for example, 1/2 appears here, and it also appears here under 2 over 4. It'll also appear in the next row as 3 over 6. And of course, for example, in an extreme case, 0 is appearing in every row, 1 is appearing in every row. So there's a lot of duplication here. We are listing all the rational numbers this way, but there's a lot of duplication. But this is a very good way of thinking in terms of the complexity of the rational numbers, in terms of thinking of them as being arranged in levels. That's an interesting, very simple idea. So let's make a definition. Let's say that a rational number r, say in the range 0 to 1, is of level n precisely when the reduced form of r is m over n. In other words, when the denominator is n when we've reduced it into sort of standard form. So this n is always going to be a natural number. 1, 2, 3, 4, and so on. Because I remind you that even if we have a negative number, the standard form of it, we agree, involves positive denominators. We always put the negative sign, if there is one, up in the numerator. So for example, 0 over 1 and 1 over 1 are of level 1. 3 over 7 and 143 over 7 are of level 7. Of course, this is not between 0 and 1, but actually the definition applies to any rational number r. Once you reduce it, you just look at the denominator and say it's of level n, where n is the denominator. These numbers, 3 over 4, minus 2 over 8, 42 over 24, they're all of level 4. This one is obviously of level 4. Why is this one of level 4? Because it's the same as minus 1/4. There it's in reduced form, and then the denominator is 4. Here there's a common factor of 6. If we divide that out, we get 7 over 4. So again, it's of level 4 because in this reduced form, there's a 4 in the denominator. This now brings us to the interesting idea of a Ferri sequence, say denoted f sub n. The Ferri sequence, f sub n, consists of all rational numbers r in the interval 0, 1, which are of level 1 to level n, in order, in increasing order. So we're looking not just at the numbers of level n, but the numbers that are of level anything up to and including n. So it could be level 1, could be level 2, could be level 3, all the way up to level n. We're going to put all those numbers together, and then we're going to order them in increasing order. So the Ferri sequence of level 1, f sub 1, just 0 over 1 and 1 over 1. With f sub 2, we add in the numbers of level 2. So we only get one new one, 1/2, because we already have 0 and 1 from the previous level. Then when we go down to f3, we're considering all numbers of levels 1, 2, and 3. So we include 1/3 and 2/3, and we have to put them in order. We get something like this. So f sub 4, 0, 1/4, 1/3, 1/2, 2/3, 3/4, and 1. So these are all the fractions between 0 and 1 whose denominators are less than or equal to 4. Here are all the fractions with denominators less than or equal to 5. Here are the ones with denominators less than or equal to 6. And we can keep on going. So this is a fairy sequence. Now, a rather interesting property of these is that we can go from one to the next in a very simple way by using the idea of a median. What we do is we look along the list and we look at adjacent or neighboring elements in the sequence, and we find the medians of those neighbors. And if we find a median that has a denominator less than or equal to the next level, in this case 5, we'll include that. And we'll put it exactly between the two adjacent neighbors that they came from. So the median gets fitted between its two parents, so to speak. So for example, 0 and 1/4. Well, 0 is really 0 over 1 when you write it in reduced form. So 0 over 1, 1 over 4, the median of that, I remind you, you add the numerators, you add the denominators, you can get 1 over 5. So we insert 1 over 5 between 0 and 1/4. The median of 1/4 and 1/3 would be 2 over 7. But 7 has a denominator which is bigger than 5, so we're not going to include that median. So we'll just have 1/4 and 1/3. However, the median of 1/3 and 1/2 is 2/5. That is allowed because its denominator is less than or equal to 5. So we put in 2/5 and we put it in between the 1/3 and the 1/2. So to go from one to the next is relatively simple. It just involves inserting some medians, going through, seeing which medians have denominators or are of level n, and inserting them in the right spot. So for example, we've also inserted 3/5 between 1/2 and 2/3, and we've inserted 4/5 between 3/4 and 1. These are the fairy sequences, and this is the lovely rule involving medians that allows us to go from one sequence to the next sequence. The fairy sequences have a lovely connection to a topic that we've discussed much earlier in this series, to the topic of Ford circles, which goes back to Math Foundations 14. So you can have a look at Math Foundations 14 and remind yourself about what a Ford circle is. But let me tell you, in any case, this is a way of visualizing rational numbers by assigning to every rational number a circle in the plane. And I'm going to draw the Ford circles in a slightly different way that I did in Math Foundations 14. In that video I had the smaller circles up here. I'm going to put them down here today. So here's the usual x-axis, 0, 1, 2, 3. Y-axis, height 1. And the first thing that we do is we draw a circle centered at each of the integer points, and that circle has diameter 1. So it goes up to this line y equals 1. And these circles are nicely fitting together. They're just touching there. One of them centered at each of the integer values. Now what we do is we extend that picture by drawing more circles. So for any point r, any rational number p over q, where p and q are in reduced form, we're going to draw a circle above that point with diameter 1 over q squared. So for example, over the point, or the number 1/2, we're going to draw a circle just sitting on the line right above that point, whose diameter is, well, we have to take the denominator, which is 2, and square it. So diameter 1/4. That means that this circle will go up to the line y equals 1/4. And that's the same size as this circle above 3/2 or above 5/2. And then it turns out that this circle is exactly tangent to not only the x-axis, but also to these bigger unit circles that we had drawn previously. So it just fits right in there in a nice way that was studied by the great Greek geometer Apollonius several millennia ago. Okay, but we do that not just for a half, but we do that for any rational point. So for example, for 2/3, we're going to draw a circle whose diameter is 1/9, because the denominator here is 3, and we're going to square the denominator, so it's 1/9. So this line here, the red one, is the line y equals 1/9. And that's just the top of this circle here over 1/3, this one over 2/3, this one over 4/3, this one over 5/3, and so on. Okay, and then say the next biggest circles that we're going to draw, the ones over 1/4. They're going to have diameter 1/16. There's one there, and there's one there. And there's also some more over here. The pattern repeats with every integer, so you can just look at the pattern from 0 to 1. You see pretty well everything there is to see. So what we get with these forward circles is there's completely remarkable phenomena that all of these circles that we draw are disjoint. They may be tangent, but they don't actually overlap. Okay, they don't actually overlap. And, well, the Feri sequences that we just talked about in the previous page are intimately connected with this picture. So the Feri sequence Fn is all those circles meeting y equals 1/n² over 0, 1. So what we do is we look at a line, say the line y equals 1, and that touches two circles, the 1/0 and 1, so that's the Feri sequence F1. Then when we go to n equals 2, we're talking about the line y equals 1/4. There it is right there. And as we look across here, we bump into first this circle, and then we meet this circle, just tangentially, and then this circle, corresponding to 0, 1/2, and 1. We go down a little bit further to 1/9, and we get 0, 1/3, then we cross the 1/2 circle, then we touch the 2/3 circle, and then we get to the 1 circle. So we're getting that Feri sequence, 0, 1/3, 1/2, 2/3, 1. If we went to the next level down, which would be height y equals 1/16, then we would touch some more circles. We would touch this 1/4 circle and also this 3/4 circle. And if we went one more, we would touch the 2/5 circle, also the 1/5 circle, which I haven't drawn. Maybe I'll put it in there. Here's 1/5, and also on this side, 4/5. So that's what you get when you look across all these forward circles at a certain height. We're getting the F5 Feri sequence. So what we see here is that the further down we go, the more detail we see, the more of these small little bubbles corresponding to bigger rational numbers we get. The rational numbers form this endless foam of increasingly small little bubbles, more and more of them, finer and finer structure. And the further down we go, the more of them we pick up. It's a little bit like having a magnifying glass or a microscope. We're looking in more and more detail. We can see more and more points. The points that we're actually seeing correspond to rational numbers with bigger and bigger denominators. So they're in fact getting more and more complicated, more and more difficult to write down. So this is the deep structure of the rational numbers. It's a very deep and interesting structure. And there's probably a lot more to say about it. In fact, next time we're going to look at another aspect of it, another very classical and beautiful object or construction that's intimately connected with this deep structure of the rational numbers. We're going to look at the Stern-Brokow tree, also going back to the 19th century. And it'll give us yet more insight into these rational numbers and the beauty and the depth that they enjoy. So please give this some thought, that it's really rational numbers which mathematics is all about. And when we can orient ourselves in that direction, then a lot of doors open up in front of us. And a lot of new, rich developments with a number theoretical aspect become visible. Right, so next time, Stern-Brokow tree. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.